Everything around you is built from something far smaller than imagination. Deep within matter, the laws of reality start to change. Welcome to the subatomic world. What are subatomic particles? They are the tiny building blocks hidden inside matter itself. Particles so small that millions of them could fit inside a grain of dust. Scientists discovered many of these particles using powerful machines called particle accelerators. Like the Large Hadron Collider at CERN, where particles are smashed together at nearly the speed of light. But nature had already been creating these collisions long before humans existed. High-energy cosmic rays from space constantly strike Earth's atmosphere, creating showers of subatomic particles above our heads every second. But these particles possess strange properties unlike anything in everyday life. One of them is called spin. In our world, spin means rotation. The Earth spins on its axis, completing a full 360-degree rotation and returning to its original state. Simple. But the quantum world is not so simple. Let's unravel the mystery of quantum spin using the Dirac belt trick. First, consider bosons particles with whole number spins like 0, 1, and 2. When rotated by 360 degrees, they return perfectly to their original configuration, unchanged. But fermions behave differently. Fermions have half-integer spins such as 1/2, 3/2, etc. Using the Dirac belt analogy, if we rotate one end of a belt by 360 degrees while keeping both ends fixed, the belt becomes twisted and cannot return to its original state. Only when we continue the rotation to 720 degrees does the twist disappear, and the system returns to its original configuration. This is why particles are classified differently in quantum physics. Bosons and fermions behave in fundamentally different ways under rotation. Unlike classical rotation, spin can take only discrete values. Particles with half-integer spin are called fermions, while particles with integer spin are called bosons. And as particle accelerators became more powerful, more and more particles were discovered, leading to the deeper classification of matter in the Standard Model. From simple spin behavior to an entire particle zoo. Each discovery revealing a deeper layer of reality. What is matter really made of? If we zoom deeper and deeper into the universe, beyond molecules, beyond atoms, and even beyond protons and neutrons, we eventually reach an astonishing world of elementary particles. At the most fundamental level, matter is built from tiny particles called quarks. These quarks are unimaginably small, and inside atoms there exists enormous empty space compared to their size. Quarks are considered elementary particles because, as far as we know, they are not made of anything smaller. Quarks combine together to form composite particles, the building blocks of the visible universe. But nature has a strange symmetry. For every particle, there exists an antiparticle. Matter has antimatter. Quarks have antiquarks. An antiquark behaves almost like a normal quark, except some of its properties, such as electric charge and color charge, are reversed. Nature, however, does not allow quarks to combine randomly. Only certain combinations are permitted. A meson consists of one quark and one antiquark. A baryon consists of 3 quarks. An antibaryon consists of 3 antiquarks. And then there are leptons, such as electrons, which contain no quarks at all. But early quark theory faced a serious problem. According to the Pauli exclusion principle, no two identical half-integer spin particles can occupy the same quantum state simultaneously. This rule applies not only to electrons, but also to quarks, since quarks also possess spin 1/2. Now consider the particle known as delta++. It appears to contain 3 identical up quarks existing in exactly the same state. That should have been forbidden. So how could such a particle exist? In 1964, physicist O. W. Greenberg proposed a revolutionary solution. He suggested that quarks possess an additional hidden property called color charge. Quarks not only come in 6 flavors: up, down, charm, strange, top, and bottom, along with their corresponding anti-flavors. But they also come in 3 colors: red, green, and blue. And antiquarks carry anti-colors: anti-red, anti-green, and anti-blue. This completely changed the picture. Nature also imposes another remarkable rule. All naturally occurring particles must be colorless overall. A baryon achieves this by combining red, green, and blue together. Just as red, green, and blue light combine to form white light, quarks combine to produce a color-neutral particle. And this elegant idea became the foundation of quantum chromodynamics, the modern theory describing the strong nuclear force. Inside a proton, 3 quarks are constantly exchanging gluons. Gluons are the force particles of the strong nuclear force. When a quark emits a gluon, its color charge changes instantly. Another quark absorbs that gluon and changes color too. For example, a red quark may emit a red anti-blue gluon and become blue, while a blue quark absorbs that gluon and becomes red. This continuous gluon exchange acts like an invisible glue, binding the quarks tightly together and keeping the proton stable. When we look deeper into matter, beyond atoms and nuclei, we enter the world of elementary particles. These particles may be extremely small, but they are not identical. Each particle has specific characteristics that define its identity and behavior. These characteristics are called particle properties or quantum numbers. They help us understand how particles interact, transform, and combine to form the universe around us. Electric charge is a fundamental property of particles that determines their electromagnetic interaction. It is quantized, meaning it exists only in fixed units of the elementary charge E, not in continuous values. In the particle world, we observe charges like +1, 0, and -1. But at a deeper level, these particles are made of quarks, which carry fractional charges. These fractions combine to give whole particle charges. For example, a proton is made of 2 up quarks and 1 down quark. Adding their charges gives +1. A neutron is made of 1 up quark and 2 down quarks. Adding their charges gives 0. Similarly, for pions, pi plus u anti-d gives +1. Pi minus d anti-u gives -1. And pi 0 is neutral with 0 charge. Thus, fractional quark charges always combine to produce whole integer charges for observable particles. Strangeness is a quantum number associated with the presence of strange quarks inside a particle. Each strange quark carries a strangeness of -1, while each anti-strange quark carries a strangeness of +1. The total strangeness of a particle is simply the sum of the strangeness values of all its constituent quarks. Baryon number is a quantum number that distinguishes baryons from other particles. Each quark carries a baryon number of +1/3, while each antiquark carries -1/3. The total baryon number of a particle is the sum of the baryon numbers of its constituent quarks. Thus, all baryons such as the proton, neutron, lambda, and Xi have a baryon number of 1, while mesons such as pions have a baryon number of 0. Baryon number is conserved in particle interactions. Another important quantum number is spin, an intrinsic form of angular momentum carried by every particle. Based on their spin values, particles are classified into two main categories. Fermions have half-integer spin values such as 1/2, 3/2, and so on. These particles make up matter. Examples include quarks, electrons, protons, neutrons, lambda particles, and Xi particles. Bosons have integer spin values such as 0, 1, 2, and so on. These particles are responsible for mediating forces. Examples include photons, gluons, and the W and Z bosons. Isospin, or isotopic spin, is a quantum number used to describe the similarity between particles that interact through the strong force. The concept was introduced because the proton and neutron behave almost identically under strong interactions. They are treated as two states of the same particle, called a nucleon. Leptons are a family of fundamental particles that do not participate in the strong interaction. They have spin 1/2, making them fermions, and are considered elementary particles because they have no known internal structure. The lepton family consists of 6 fundamental particles arranged in 3 generations. The charged leptons are the electron, muon, and tau, while their corresponding neutral partners are the electron neutrino, muon neutrino, and tau neutrino. By the 1950s and early 1960s, physicists had discovered many new particles in cosmic rays and particle accelerators. The growing number of particles created a need for a systematic method of classification. In 1961, Murray Gell-Mann and independently Yuval Ne'eman proposed the Eightfold Way, a classification scheme based on symmetry principles. The Eightfold Way organized hadrons into patterns called multiplets according to their properties, such as charge and strangeness. In the Eightfold Way diagram, particles are arranged according to their charge and strangeness. The horizontal lines represent particles with the same strangeness. As we move upward or downward, the strangeness value changes. The diagonal lines represent particles with the same electric charge. Particles lying on the same diagonal have identical charge values. As we explore these patterns, we encounter octets, decuplets, and other particle families, each revealing an underlying symmetry in the strong interaction. What first appears to be a collection of unrelated particles now emerges as an organized and elegant framework, the Eightfold Way.